sparse matrices from SciPy, and that already gave us tons of gains. So I think once we think about how to do this in a more like smart way, I think part of that bottleneck is just going to disappear.
Very interesting. Thanks.
Any other questions, like quick question? Otherwise, I will invite everybody to go to ask Ben questions in Slack. Okay, I don't see hands. So thanks a lot, Ben.
Yeah, thank you.
And now we are moving to the next contribution by Matteo Marchegiani. Matteo, you connected? Yeah, perfect.
Yes.
And we will be listening about PocketCoffea. So.
Yes. Can you see my screen?
Yes, we can see a screen.
Great. So let me start with this tutorial example on PocketCoffea. So first of all, what is PocketCoffea? It's a Python package built using the pre-existing Coffea package, and we use the standard Coffea processor scheme, and we basically built a configuration layer on top of these tools. So here I left some links. You can find the GitHub repository of PocketCoffea, one with the analysis configurations and the documentation. Today,
yes. Sorry, can I ask you to make a bit more like larger scale?
Yeah, sure.
Yeah. So just in case. Thanks. Sorry.
No problem. Now you should be able to see.
Perfect.
So basically, what we want to show today is an example using the CMS open data datasets from the 2012 dataset at 8TV. And we want to implement a toy analysis of Z to mu using these publicly available datasets. So first of all, PocketCoffea comes as a package, so we can import it, of course, in our shell, and then to start with the analysis, we have to define the analysis processor. In PocketCoffea, there is a defined structure for the processor, so there are some fixed, some well-defined steps that we have to follow and define. So the first one is that we scheme the events. So we apply generic Lumi masking, applying the triggers and the loose selection to reduce the numbers that the number of events that we are going to process in the next steps. Then we have to define the object preselection. So which are the good objects that we use in the final analysis. Then there is an analysis preselection, an event preselection, and this is the main preselection that you apply. And on top of this, we can categorize. So we can further split this selection into multiple categories. For example, when one has to define signal and control regions. Also, an important step is Monte Carlo reweighting. So we know that our simulation needs to be corrected and there are many corrections to apply. So there is a custom tool implemented for that. And of course, filling the histograms for all the categories. In this demo, so usually what we do is to define a processor by importing the PocketCoffea base processor ABC, which is an abstract class. For today's demo, we implemented a custom, an open database processor to cope with the differences between the run2 datasets and the open data datasets. So there was some difference in reading the files, but the idea is the same. So we have this open database processor that is imported from this file-based processor that you can find in the folder. And then we derive a class that we call ZMU based processor, and we override some methods of this class. In particular, we have to define the object preselection. So you can see that here we are defining some cuts on eta and pt of the muon on the isolation. And then we return some good objects. So the muons passing these masks. Then the second method is to define common variables after preselection. And we do this to define the dilepton object and to construct the dilepton invariant mass, and also a method to count the objects. And I suggest you after to look at the implementation of Open Database Processor in this file to have more insights in the implementation. But so once we define our custom processor, we have to define the analysis parameters. The way the parameters are managed is by using the OmegaConf package. This is a Python package that is able to compose different parameter files in YAML format, and we can update some default parameters with custom parameters. Indeed, in PocketCoffea we have these nice defaults that are basically all the defaults for the run-to analysis in CMS. But for specific applications, of course, we can override these parameters with our custom files that at the moment are stored in this params folder. And once we call this function, the parameters are updated, and here you can have a look at the keys of this dictionary. So there are all the pile-up corrections, HLT triggers, even the plotting style. So basically everything in one dictionary. And here you can have a look. Let me run this cell. Yeah, and you can have a look at the parameters. So it's a big dictionary with all the parameters that define the analysis. And of course, this dictionary is saved on disk. So when the user wants to reproduce the analysis, or the user forgot about which parameter they used on that specific run, it's all stored in this dictionary. So this enhances reproducibility. So this is for the parameters. Then one has to define the datasets of the analysis. And the datasets are defined in some JSON files that are now stored in datasets. And these files come with the metadata and the file list. The file list, of course, it's the list of files. In this case, you can see that I just loaded this JSON file, and there is only one file in the list. There is a name for the sample and the metadata. So we know the sample name, the year, if it's Monte Carlo, which if it's data, we know the era. So this is an example of how the dataset is handled. Also, an interesting feature is the subsamples feature that you can see here. So one of the applications of subsamples is when one has to split a Monte Carlo sample or a data sample into different pieces, different parts. For example, here as an example, we are splitting this Monte Carlo sample, Drellian Jets 2LL, into different subsamples, depending on the number of muons in the event. And here we define a key, so which is the name for this subsample, and the list of cut objects. I haven't introduced them yet, but I will tell you more in the next cell. But basically, these objects define the selections that we apply for this specific subsample. So once we define the datasets, we can go to the preselection and scheme, preselection and categorization. And here I will introduce the cut objects. So the cut object is basically it's a simple object that carries a function and parameters. Now I explain you. Here we are defining the daemon function, and this can be used to define multiple cuts. For example, here below, I'm defining 3 different cuts using the daemon function. Because the function is written purely parameterized with this params dictionary. And then with the cut object, we just need to pass the parameter dictionary, the function, and then this object will have a built-in method to get the masks, and this is handled within the framework. But the idea is that we can reuse this function just by changing the parameters. So what I'm doing here, for example, is to define a signal region around the Z boson mass window for the dilepton mass. Then I'm defining a MLL, a region at low invariant mass, and the region at high invariant mass as control regions, as a toy example. And after we define the cut objects, we have to define the weights that we want to apply and the systematic variations. So here we have 2 dictionaries. This is handled inside the framework. And basically in the configuration file, we just have to list the name of the weight that we want to apply. So for example, in this case, we are applying the common gen weight reweighting for Monte Carlo, the luminosity times cross-section rescaling. And also we apply this extra muon scale factor, muon isolation scale factor. And below in the variations dictionary, you can see that I'm also including this muon scale factor. So the difference is that between these 2 dictionaries is that in the weights, I define the weights that I'm going to apply. And in the variations, I'm defining the variations that I'm going to store in the final histograms. So once I define this, we can now load the configurator. So we have these configurator objects that takes all these pieces that I described before and builds an object that is also doing operations on parameters on datasets and will spit out the inputs for the Coffea processor, basically. And here, so you see that I'm also passing the workflow, the scheme cuts. So for the scheme cut, I'm asking for 2 muons and also a trigger, a double muon trigger. This is the preselection that I am applying. And here I'm categorizing depending on the dilepton invariant mass as I described above. Here, the extra step is the variables dictionary, where we define the histograms. Here with muon hists, I'm using a nice default that we have in the histograms module. And this will trigger the production of all the standard muon histograms like PT, eta, phi, and mass. While here, of course, the user can define custom histograms. Like here, I want to define a dilepton mass histogram, and I do it with this histconf object and this axis object that is basically passing information to the hist manager within PocketCoffea on how to build the histograms and their axes. Now you saw that I just run this cell and I save the config. And so the config now is stored in the output folder for reproducibility. Now we define the config. So we want to run the analysis in Coffea. There are many options. Like you saw in the previous talk, of course, when we want to do a full-scale analysis in CMS, we can't run it locally. We need to scale out on a cluster using a scheduler, like using Dask on a Slurm cluster. But for testing and for small processors, we can run locally with the iterative executor or with futures. With the first one, it's just an iterative execution with no parallelization, while in futures we have parallelization. To use this runner, so there are some classes implemented in PocketCoffea, and we pass parameters with these dictionary run options that in the case of submission of jobs, it defines all the parameters like which image to use, the queue, the wall time. It's important the chunk size, which is the number of events in each chunk that the processor will process. Of course, at the moment, we just want a simple example, so we will run the futures runner locally with 32 CPUs, because as you can see on this container machine, we have 48 CPUs, so we can run on 32 CPUs. So what I did now was to initialize this futures runner that will handle all these run options, and with the run method, this will trigger the execution of the analysis. Now I will do it. And you can see that I'm passing just the file sets, the processor instance, and then, okay, there are additional parameters that I pass to this runner. Now you see that the processing progress bar is going on, and it's very quick because we are reading just the CMS open data, so it's very slim NanoAOD files with a few branches, so it's very quick. And okay, there are some warnings because these are Coffea warnings, because some branches that usually are in the NanoAOD file are missing, but this is just due to the structure of the file. Sorry for the large printout. But basically, at the end, we get the output saved in our output folder, this output.coffee file. So let's see what we are left with in our output folder. We have 4 files: the parameters dump, the 2 versions of the configurator file, and the output. So the output is storing, of course, the histogram files, the cut flow dictionary, and metadata of the samples, while config.json is a human readable format for the config file. And there is also a pickle version of the configurator, such that one can just load this file and rerun exactly the same analysis with the same configuration. And also the parameters that I described before are also saved in a YAML file. Okay, and now we can inspect this output. So let's see, we can load this Coffea file, and these are the keys. So we are saving the sum of gen weights for Monte Carlo, the sum of weights, the cut flow, the variables. So this is the dictionary for histograms. Columns is the optionally one can just dump the n tuples, for example, is needed if one needs to do machine learning trainings, so we can dump the n tuples, and also the metadata. So for example, you can have a look at the datasets metadata, and you can see that this is just saving the metadata that is initially stored in the JSON dataset file, and we have it here for reference. This is the cut flow dictionary. So for each selection and for each sample, we save the number of events. So this is actually, it's not Monte Carlo weights, it's the actual number of events that you are reading. And you can see that we just processed 30 millions, if I'm not mistaken. Yeah, 30 millions Monte Carlo events and 26 million data events initially. And then you can see the cut flow. So the number of events in the final selection, of course, is less. Then after the cut flow, once we have the output, we can produce the data Monte Carlo plots. This is handled by the plot manager object. And I will show you how. This object, we just pass the output dictionary that we just obtained, also with the metadata and some other parameters. And we will get this plotter object. This plotter object stores basically shape objects. We call it shape, and a shape is a histogram. So here you can see the dictionary of this, the dictionary of shapes. So we have, for example, the muon, good, eta, eta histogram, and it's an object of type shape. So as an example, we can save, let's look at the shape for MLL 2012. So this is the dilepton mass, and it's a shape object. And there is a nice method to just plot data Monte Carlo with the default CMS layout. You can see here, I'm just, you just have to pass the category where you want to plot. And we get this plot. Maybe let me put less zoom. Sorry about that. Okay. And here we can see the output plot that we get with the default, with the CMS defaults. You can see that the Monte Carlo that initially was a single sample is split into 3 samples. Of course, it's mostly red, so the 2 muons subsample is dominant in the inclusive region. And also we are plotting the systematic uncertainty and data. And then we can, for example, plot in the signal region. We plot in the signal region, also with the dimuon cut, and we are in the Z boson mass window. And then, for example, we can plot at high mass. Sorry, no, this is the signal region. And then we can go at high mass. And you can see that we have the plot at high values of MLL. So now, one thing to mention about the systematic uncertainties. How do we handle them? There is a dedicated object, systematic uncertainty, and we can get it directly from the shape object. So, for example, here I'm saying I want to get the muon scale factor systematic in the inclusive category. And here instead I want to get the MC stat, so the statistical uncertainty on Monte Carlo. And then I'm plotting the muon scale factor uncertainty. And so there is this built-in method that is very useful when one has to check the shape effect quickly of some systematic. And you can just plot nominal the variation up and down on the same plot. Also a nice feature is that these systematic objects can be added, and there is the built-in summing quadrature. So if I do syst, so if I'm summing the muon scale factor systematics plus MC stat, I get this object, another instance of the systung class, which carries the summing quadrature of these 2 systematic uncertainties. And for example, then I can do dot up and I get the up variation. I can do down, I get the down variation. The nominal is stored. And so this is how the systematic uncertainties are handled internally in the plotting. So I'm at the end of my notebook tutorial. Of course, I try to condense in a notebook how to do a CMS analysis, which is a very large topic. So this is just an example, a glimpse of an analysis. And there is also some other steps that I left here. For example, for fetching the datasets from Das and Rucho with a nice Python function. which is how we actually get all the list of datasets for our analysis. But I leave you here this as an example, as an exercise, if you want to try it. So yeah, let me know if there are some questions.
Thanks a lot, Matteo. Okay, Alex, thanks.
Thanks a lot for this overview here. I have a question that is sort of like future facing. As far as I see, a lot of the design is kind of built around the way that Coffee approaches things and sort of like adds higher level interfaces and additional functionality. Now with Coffee changing with Coffee 23 and Dask Awkward, do you have a view of what this would mean in terms of evolution here for PocketCoffee?
Yeah, thank you for the question. Yeah, indeed, we are following very closely the Coffee 2023 release. So the quick answer is we haven't checked yet the impact of this update, but of course, with new features in Coffee 2023, we can probably also update PocketCoffee with newer features. What I know will come from Coffee 2023 is the tasks, is the task graph at the level of the processor. So now there is an optimization at the level of splitting into chunks, parallelized execution of chunks. While with Coffee 2023, from my understanding, there will be these task graphs in the single operations that you apply to the events array. But yeah, to answer like in PocketCoffee, we don't know yet what will be. Of course, we hope that I think it will be still compatible, but maybe there are some features that we can implement better, and we can keep an eye on the updates.
Thanks. Yeah, I'm curious to see where this goes.
I see David, who is also one of the authors. Do you want to comment something?
No, I just wanted to add one thing on top. Thank you, Matteo. I think your answer is completely correct. But we already checked a bit, and let's say the changes on the infrastructure that we built on top should be completely feasible in Dask. So one of the biggest hidden, let's say, tool here is the histogram filling class that is kind of doing the huge loop of systematic weights and histograms automatically for the user. And that's probably where we need to put more work to make it work for Coffee 2023. But in principle, it should still work with the same design.
Perfect, thanks. There's one more question from Maciek.
Yes, just quickly, also kind of future facing. So as more of these like Coffee abstraction layers are emerging, I was kind of wondering where you see the future of these tools. So personally, I come from the Fast Carpenter project, which has a lot of overlap with this. I was wondering if you kind of see in the future maybe consolidating those efforts into something that kind of picks the best features of all of them and maybe is released alongside a central Coffee distribution or something like this.
Yes. Yeah, thank you for the question. So the future, of course, we will be supporting this tool because there is already interest in CMS to try this tool and implement the analysis using PocketCoffee. In CMS, it's already centralized somehow within the CAT, the Common Analysis Tool Group. And regarding implementing features in Coffee, of course, if there is something that is not specific to PocketCoffee and can be generalized to Coffee, we are happy to contribute to Coffee and make it general to Coffee, not only to our configuration framework. So yeah, and I think this already happened. Like Davide made a contribution to Coffee on this DAS and Rucho datasets handling. This is an example. It's not PocketCoffee specific. Like everyone